Good to go. So today, our presenter of the day is Raissa Estrela. She's currently a NASA postdoctoral fellow at JPL. She started her history in astronomy by getting a physics and ecology undergrad degree at University of Natal in Rio Grande do Norte, in Brazil. And then she did her master's and PhD studies in São Paulo at Universidade Presbiteriana Mackenzie. And now she moved here to JPL to continue her work in studying the atmospheres of exoplanets. So I hope you all enjoyed the talk.
Thank you very much, Henrique. And I would like to start. Well, thank you both for helping out with these technical issues and apologizing the audience for the waiting time. But I'm glad I'm here today. I live 4 minutes by car from here, so it's a great opportunity to be here talking to all of you. I always wanted to visit Carnegie, so I'm very happy to be here. Thank you for inviting me. So I'm Raissa Estrela. I'm a NASA postdoctoral fellow at Jet Propulsion Laboratory here in Pasadena. And today I'm going to talk about exoplanets' atmospheres. We're going to look into trends, evolution, and habitability. Most of the work that you're going to see here today, it's part of my PhD and also some work that I continued during my postdoc at JPL. Well, thanks largely to missions like COHO and Kepler, we know that we have discovered more than 5,000 of exoplanets. And we know that most of these planets, they have a size that varies between the size of the Earth and the size of Neptune. And because of that, this population of planets that you see here that were mostly discovered by Kepler, we call them super-Earths and sub-Neptunes. And this kind of planets, we don't see them in the solar system. So they are very, very innovative for us. And we are now moving forward into the characterization of these exoplanets' atmospheres. And when we point to the telescopes like Hubble or ground-based telescopes, we want to know if these planets, they have an atmosphere, and if they do have an atmosphere, how much envelope do they have? And is it a primordial envelope, or is it a secondary envelope, or are these planets basically a backhaul planets that has no atmosphere at all? So in order to understand the observations that we take today with these telescopes, we need to understand about many factors that can play a key role in the evolution of this planet and to the outcome of the atmosphere that we see today. And as you can see in this plot, there are many factors that can play a key role during the planet lifetime. So we have bombardment, we have migration, we have geophysical process, we have the presence of magnetic field, if there is one, and also the presence of life. And if you go even more back in the planet lifetime, you're going to also see that stellar activity can play a key role, especially when the star is younger and is more active. And this effect from the stellar activity can lead into the escape of the primordial atmosphere of the planet, the atmosphere that the planet collects during the formation time, the gas that collects from the planetary, the proton nebula, which is basically atmosphere composed of hydrogen and helium. So we see evidence of this evolutionary process when we look into the exoplanets population. So if you are not very familiar with exoplanets, this is a very famous plot. And this is this planet size distribution of the small planet population. And what we see here is that there is a gap that divides this population of planets into two. So this gap is around 1.7 Earth radii. And what we see is that there is a population on the right side that have larger radii. And this population, they likely still hold a hydrogen helium envelope. While the population on the left is more around Earth-like radii. And this population, we believe that they are more consistent with a rocky population. And the gap that we see in the middle, dividing the populations, is what we call transition region. And it's an observational motivation for atmospheric escape processes that could be shaping this population. So there are two atmospheric escape processes. One is photoevaporation, which is basically XUV induced, that it would strip the envelope of these planets. And the other process is core-powered mass loss, which is internal heating of the planet that can also induce into the escape of the envelope of the sub-Neptunes. So this transition region is basically sub-Neptunes planets that would have lost their primordial hydrogen helium envelope due to the XUV fluxes coming from the host star. Just a reminder here that this population of planets, they are mostly orbiting very close to the host stars. So it's not like our solar system. They're orbiting very close, so they're way more, so they can feel way more the effects coming from the host star. So the photoevaporation, which is this XUV-induced escape, would lead to the transformation of sub-Neptunes into super-Earths. So the super-Earths, they could be backcore planets with no envelope, or they could be a rocky planet with some hydrogen helium remnant envelope. So when we look back into the exoplanets, small planets population here, we see that these rocky planets, they could have two possibilities of origins here. One is that they could be photoevaporated cores of sub-Neptunes, and the other one could be something that's more similar to our solar system evolution. So we have this question about terrestrial exoplanets. Are they remnant cores of sub-Neptunes due to atmospheric escape? Or are they shaped in a more similar way to what we see in our solar system that formed planets like Earth and Venus? So to understand about this small planet population, we took a sample from the NASA Exoplanet Archive. So every point, that single point that you see here is an observed planet. And we will look at these planets into three factors. One is insolation that you see in the upper plot, and the other one is density and radii. So what we observed here is that there are two trends. If you look in the upper plot, the insolation levels, the more large is the circle, the more insolation these planets receive. So you see that there is a trend here, if you can see my mouse pointing, of large insolation planets, while there is another trend, around here, of very, very low insolation planets. So the very low insolation planets, they seem to follow a common trend with the solar system objects, which are represented by star symbol, while the large insolation planets, they seem to form a piecewise continuous with the sub-Neptunes. So this population here, the blue one with high insolation, they're likely to be remnant cores of sub-Neptunes due to photoevaporation process, like I mentioned before. While the ones with lower insolation, they maybe are formed, they possibly share a common formation mechanism with the solar system objects, where we know that impacts play a key role in shaping the terrestrial planets in our solar system. So we see that there are two possibilities for terrestrial planets in the exoplanets population. And now we have the following question. So are these populations with high insolation really photoevaporated sub-Neptunes? And to answer this question, we need to go into to compute the photoevaporation for this sample. So we take the highly radiated terrestrial planets, the same from the sample before, the sub-Neptunes, which are the green ones, so the real sub-Neptunes because they really have hydrogen and helium. And we're going to track their evolution using the mass and radius diagram. And of course, if you want to track the evolution, we need to know how these planets were back in time before they lost any envelope. So what I do here is I estimated the primordial population, and then I put them in photoevaporation models to estimate how much envelope they lost. And I will get this percentage of envelope loss. So now we go back to the mass and radius diagram, and we put the current population of highly radiated planets and the current population of sub-Neptunes, and we track them. So this dashed line that you see in the plot is tracking the current population to the primordial population that's up here. And if you look in the radius, you see that there is a dramatic change in radii. And this is because super-Earths, these highly radiated terrestrial planets, they lost absolutely almost their whole envelope. While sub-Neptunes, the green ones, they likely lost 30% of the envelope. So they also lose something. So these terrestrial planets that we see that have high insolation, they are ideal candidates to the search of secondary atmospheres because they likely lose all their primordial content. And a great example of them is this planet here, the J1132b, which has the same size of the Earth, but it has an insolation that's 19 times the insolation that Earth receives. And luckily, we have observations using with the Hubble Space Telescope for this planet. using a technique called transmission spectroscopy. Yes?
Sorry, so on the previous plot, those are theoretical traps.
Yeah, I estimated what was the primordial envelope of these planets using, so there are, I can go more in details in the end if you want, but basically I need to estimate what is the core mass of these planets and what is their current envelope. And then I go back in time using the XUV fluxes of the star in time to estimate how much they go losing these envelopes. So that's how I can track what is the primordial and what is today. So it's basically some estimates.
I would think most of them are beyond the ice line. These are all much closer.
Yes, these are much closer in.
Like evolving flux or something?
Oh, I didn't consider migration here. So I am assuming they are all in the same orbit that they are today. Mm-hmm. But yeah, it should definitely, migration can definitely play a key role here. So yeah, so we have observations using the Hubble Space Telescope for this target, the J1132b, and we use this technique called transmission spectroscopy. For those who are not familiar with this technique, is basically we are observing the transit of the planet, and during the transit, some part of the starlight can pass through the atmosphere of the planet. So this light is going to interact with any molecule or atom that's present in the atmosphere. So these atoms or molecules, they can either absorb the starlight or they can scatter the starlight. And we are going to see this scattering or absorption when we see the transit. So the atmosphere, when there is any interaction of the atoms with the starlight, the atmosphere is going to appear as an opaque disk. So, and this is going to occur at a certain wavelength range because each molecule or atom, they absorb in a specific wavelength. So when you look at the transit in different wavelengths, you can see this change in the transit depth because of the atmosphere absorption, because you're going to see this opacity of the atmosphere. So basically the transmission spectra is going to be this difference, this change in the transit depth as a function of wavelength. And if you can tell in each wavelength, you can tell something different that's happening in the atmosphere of the planet. So if you look in the visible, you can see Rayleigh scattering, and you can also see atomic absorption. And if you go to the infrared, you can look into molecular absorptions like water or methane. And there are two instruments on Hubble that we use to do that. One is TESS. So TESS, we can look into the visible portion. It goes up to the beginning of the near infrared, and the other instrument is JWST. This one is the most used instrument on Hubble, and it covers a small portion of the near infrared. And the feature that we normally look for is water, but you can also detect methane and other absorbers as well. So going back to the J1132b, this is the transmission spectra that we got using the Hubble Space Telescope observations. And as you can see here, we have some spectral features. The most prominent one is this aerosol scattering, but we also see some weak features of methane, and we see HCN as well. So in order to see this atmosphere, we know that this would need to be an atmosphere that's mainly composed of hydrogen and helium. So it's 99% hydrogen and helium, and it has these other absorbers as well. This planet is J1132b. So it's a planet that has almost the same size as Earth, and it has insolation that's 19 times the insolation of the Earth. So you can be wondering, how can such a small planet, because it's almost the size of the Earth, how can such a small planet hold an atmosphere that's basically hydrogen and helium? And it's totally, it's totally reasonable to think that, because if you look into the escape velocity of the planet, you're going to see that the J1132b has almost the same escape velocity as our planet. So this means that this planet does not have sufficient gravity to hold hydrogen or helium in its atmosphere. So what's happening here is that we would need a replenishment of hydrogen to keep the hydrogen in the atmosphere and counter the thermal escape. So what has been proposed for this planet is an outgassing mechanism through volcanism. So this planet probably accreted or got some hydrogen and helium trapped in its mantle during the formation. So during the same time that the planet accreted hydrogen and helium to form the primordial atmosphere. So some of this hydrogen got dissolved in the magma. And we believe this planet is very hot inside because this planet is tidally locked with the host star. So there is a tidal heating that could be keeping this mantle liquid. So this hydrogen it was originally trapped in the mantle could now be released back to the atmosphere through outgassing. And we had a collaborator, Paul Riemann from University of Oxford, that did some outgassing, basically dominated by hydrogen. And his models indicates that the hydrogen-dominated magma is the one that better fits our data that you see in blue, compared to a nitrogen-rich atmosphere, which provides a very relatively poor fit here. So this outgassing volcanism, outgassing due to volcanism that we see in this planet would be very different from what we see in our planet, because in our planet, most of the outgases of the gases here are oxidized gases, while in this planet would be a way more reduced gases. So when we see again, have a look again in the J1132 transmission spectra, we see that the most important feature here to detect an atmosphere is this aerosol scattering. This is slope that goes towards short wavelengths. And aerosols, or haze, as we commonly call them, they are very common in our solar system as well. So this is not new for exoplanets. They are very common in the solar system. We see haze in Jupiter's atmospheres, and we also see haze even in small objects in our solar system, like Titan has a chain of reaction that form organic haze. And even in Pluto, there is a smooth layer of haze as well. And when we look in the transmission spectra of multiple exoplanets, as you can see in this figure here, we also see that slope that, the same slope that we see in the J1132 towards the short wavelengths. We see this scattering. That's basically due to the presence of haze or condensate clouds like silicate can also induce this scattering in the very upper layer of the atmosphere of the planet. So anything that's below this layer of haze and clouds, for example, water, can be muted by the presence of clouds and haze. So if you see some of these planets like WASP-31b or WASP-12, you barely see the water feature that's expected at 1.4 microns. So this bump that you see here is water. So some of them you don't see. And this is because of the layer of clouds and haze that's way upper in the atmosphere. So it's very important for us observers who want to study exoplanets atmospheres to understand about haze and clouds, because one, you can use them to detect an atmosphere, which was the case of the J1132b, but you also need to understand them because they can mess up with your observations if you want to detect water at 1.4 microns. So there is an instrument on Hubble, we call it TESS, that can provide us the visible portion. So TESS cover this portion here of the transmission spectrum, so we can understand more about clouds and haze using TESS. And TESS has two filters, G430L and G750L, that together they cover from 0.3 to 1 micron. So it covers all the visible portion of the transmission spectrum. And during my PhD, I was one of the developers of the Excalibur pipeline, where I implemented TESS in this JPL pipeline. And this pipeline, it came to provide a uniform multi-wavelength analysis of observations from Hubble and also Spitzer. So we combine those observations. We have a catalog that's up to 90 planets. So these are all public observations taken with Hubble. And we aim to build this catalog to provide comparative planetology of exoplanets. And this point is very important because most of the studies in exoplanets atmospheres, people are using different pipelines. So it's difficult for you to make comparative planetology if you're using pipelines that use different analyses. If you want to compare apples to apples, you need to process everything in the same way. So you need a uniform pipeline. So that was the reason that Excalibur was created. And the second point is because we produce transmission spectra at full resolution in the case of the JWST instrument, and also high instrument resolution in the case of TESS. And the full resolution is very important in WST3 because most studies, they also do a spectral average. And when you average the spectra, you can kind of lose the spectral amplitude. So you kind of smooth the spectra. But if you want to see exactly, if you want to distinguish between spectral features, you need to keep the full resolution of your spectra. And we also have an atmospheric retrieval package, Cerberus, which is designed to interpret the observations, to interpret the transmission spectra. So you can obtain the best set of atmospheric parameters. And we aim to make all these public available very soon, actually, I think next month, of our planet spectra and also the retrieval from Cerberus. So this is just for you to have an idea of how the Excalibur pipeline is going to look like. So every one of you here is going to have access to this portal where you can access the transit light curve. You can also access the transmission spectra and even all the data products from our pipeline. So there is a series of steps in order to obtain the transmission spectra and also the to get in the transmission spectra and interpret the transmission spectra. This is a very simple version of the scheme. It's way more complex than that. But basically, we collect the data from the JWST archive. We perform calibrations. So basically, we need to transform the 2D image into a 1D spectra. We need to remove cosmic ray, do the wavelength calibration. And once we do that, we have the calibrated spectra that you see in that corner. We can sum, we can average in all the wavelength axis to obtain the transit light curve. Or you can sum in each spectral beam here to obtain these spectral light curves that you see on the right. So this spectral light curves here is going to be, it's basically your transmission spectra. So it's the change of the transit depth as a function of wavelength. And once you have this transmission spectrum, you need to interpret it using atmospheric retrieval, which is basically, retrieval means that you're going to take the observations and use it as a starting point to interpret, to collect, gather data for interpreting the atmosphere of these planets. So this is one of the results that we have for Saturn mass exoplanet WST69b. So here you have we have the TESS data set, which is the visible portion, these two data sets, plus the WST3 data. And what we see here is that there is this huge slope, which is due to the presence of aerosols, haze, or clouds, that's covering up to 10 scale height of the atmosphere, which means that this is widely distributed in the atmosphere of this planet, going up to microbars. And because there is this huge layer of haze, the water filter that we expect at 1.4, and you can see a little bit here, is kind of muted. So the haze layer, it's muting this water filter. So this is observational evidence that haze can be widely distributed in the exoplanet's atmospheres, and also gives these, it shows the importance of including TESS data set into the interpretation of exoplanet's atmospheres. And we also perform some comparative planetology studies using our pipeline, our catalog, Excalibur. But this is only using the WST3 portion, which means that it's basically the near-infrared. So I'm not using TESS, the visible here. So we have 62 planets observed with WST3. You can see in this plot that these planets, they vary in size and also in temperature. We have planets very small and very cold, and we have planets that are large and extremely hot. And this sample is a great representation for future missions like Ariel. Ariel is a mission from ESA that's designed exclusively to observe exoplanets' atmospheres. And our sample, the gray ones, the gray points that you see here, is the top ranked targets for the Ariel mission. So our sample is covering exactly what is expected with Ariel. And also in terms of the star, we also have stars with a wide range of metallicity and also with different temperatures. So one of the studies that we did with the 62 planets catalog was to understand how common and significant is disequilibrium chemistry. So for who is not familiar, atmospheres of planets, they can be under thermal equilibrium, but can also be into disequilibrium chemistry. Disequilibrium chemistry means that it could have some photochemistry, for example, going on in the atmosphere, and it would create any disequilibrium observers that's due to the reactions, the photochemistry reactions. And most of the models of exoplanets atmospheres, they use only the equilibrium chemistry, assuming that water is the most dominant feature. That's the easiest way, compared with this equilibrium, including photochemistry. So here we included the equilibrium chemistry, and we did a statistical analysis to see what is the preference in these exoplanets targets. What do they prefer, the equilibrium or equilibrium chemistry? And what we found is that equilibrium is favored for 30% of the catalog. And when we look into the XUV flux as a function of temperature, we saw that there is a cluster of planets around here between 1000 and 1800 Kelvin that they prefer the equilibrium. And this could be because the XUV flux is kind of high here in this region, and the XUV is it would be inducing photochemistry in the atmosphere of these planets. So that could be one of the possible reasons why these atmospheres in this specific region is going to the equilibrium chemistry. Earth would be way down below, so Earth should be around here. I don't remember exactly the XUV flux of the Earth, but yes, definitely the low side, very low. These are way like, they are closing planets, so they receive way more XUV. Yeah, and the other study that we are doing, this one is being led by me, and it was recently I put on archive. It was submitted to the UpJ letters as well. So this is the same sample of exoplanet, the 62 planets. And what I did here is to take the amplitude of the spectral feature. This is an example for the target Habitability 26b. And this is the water feature. So you see there is this huge bump around 1.4. This is water. So if we take this spectral amplitude, we call spectral modulation. And we for each target, so I did for the 62 planets, and we can see that as a function of temperature to see if there is any trend of the amplitude that we detect in the spectrum of these planets as a function of temperature. Because this could, if this feature is muted, it could be an indication of the presence of clouds and haze. So what we see, these planets around here, the spectral feature that I detect. But there are other planets that basically it's like a flat spectrum, so you don't detect any amplitude. So this cluster that you see in blue here with 0 amplitude, this means that these planets, they are either dominated by cloud and haze, so you see a flat spectrum, no amplitude, or that they have high molecular weight atmospheres. So you can we can't detect high molecular weight atmospheres. So atmosphere like our planet, Earth, it's almost impossible to detect with Hubble right now. So we would see a flat spectrum like that. So, and also all the other planets that you see in this plot, we detected something. So there is the ones with 4 scale height modulations, because you can really see well any spectral feature in this plot here. So a reminder that WST3, it goes from 1.1, 1.2 up to 1.6 microns. So it's a very narrow range that we see in the near infrared. And mostly the features that we expect here is water or methane or some photochemistry product as well. But most of the works, they use water as a dominant feature, but that's not really true. It could also be another observers as well. So what I did is to take these amplitudes that we see. I exclude everything that's cloud and haze dominated, because I would like to see if there is any trend into these other targets that show some amplitude. And I calculated as index to see how much they vary from 0 to 1, 0 being the cloud dominated to 1 being the clear. So I basically divided this amplitude by the very clear atmosphere model, which is the dashed green here. And I created index. So 0, as I said, it's cloud and haze dominated, and 1 is cloud free. And what I see is that there is this quadratic trend here, is the preferred one, and indicates that planets, we expect the planets to be cloud free around 1600 Kelvin. And if you go to lower temperatures, you are expecting more cloudy atmospheres. And if you go to high temperatures, but we also could expect more cloud atmospheres, but we have very few data points in the very high temperatures, so it's kind of hard to say. But we can use this trend as a forecast, especially for future missions like Ariel or even for James Webb. We can use this trend as a forecast to find which planets, potential targets that could have cloud-free atmospheres, because these ones are the ones that we want to observe. Yes.
So the cloudiness is completely confirmed by deviation. The amplitude from
Yes. Yeah, this one, yes, I'm normalizing by the cloud-free model. So I'm taking the amplitude and normalized by the cloud-free model.
So if it's cloudy, does that show up at shore wavelengths? Is that right?
I'm not including short wavelengths here. So this is just included the 1.1 for 1.6. It's only including WST3 data. I didn't include the STIS yet. So this is for future work. I want to include the STIS, the short wavelength portion, because then we can take that scattering into account here. But as because I'm still working the STIS catalog, it's not ready yet, completely ready for that, because we need to merge STIS with WST3, and I'm working on the merging. It's not very easy to do the merge. It's not straightforward. So for future work, I'm going to include that.
For the shorter wavelength data, we know how test whether it really is.
Sorry?
The shorter wavelength data will provide a test.
Yes, exactly. Yeah, the short wavelength is decisive. It's very important here.
So you said that Earth would be in this cloudy phase.
Oh,
That surprises me.
oh no, no, Earth is not here. Oh, but wait, in the low temperature, yes. So it's hard to take any conclusion. The low temperatures. There are two trends. Possible trends for them. You see that there is a quadratic one, indicates that they would become more, low temperature planets would become more cloudy. But if you take the 40 or the polynomial, it seems that it started to increase into the clear atmosphere for low temperatures. But we need more targets around this portion to make any conclusions, like any conclusive assumptions here. But I would say that it's kind of, there are two possibilities. Although the quadratic trend, statistically, this one is the preferred one, but the polynomial also showed that could have a possible trend towards clear atmosphere for low temperature planets. So we need to populate more this portion of low temperature planets in order to really know what's going on here.
But you could calculate what the modulation of the water feature is.
Yeah.
It must be higher than 50%.
Yeah, we would need to check that. I don't know.
So that point really.
Yeah, would add a point here for sure. Yes, these two planets that you see are planets in the habitable zone. So it means that they would receive kind of the same insolation flux as the Earth, but they are not super cloud free. They are kind of in this trend that we can't really tell yet. But definitely we need to populate more this, I would say, this portion here to make any conclusions. There are some laboratory experiments that says that low temperature planets, they should be more cloud free, because the haze, you have condensated water for these planets, and condensated water could help to remove the aerosols. So they say that it should be cloud free. So maybe this trend is really towards cloud free for low temperature planets, which would be awesome, because it would be easier to observe anything in these small planets if they are cloud haze free. So I talked about haze, and haze are very important for habitability as well. So now I'm going to move to the last part of my talk, which is to understand habitability in exoplanets. So haze plays a key role in planetary dynamics because they can regulate the temperature and the radiation flux. They can also provide organic material, which can help to build blocks of life. And we know organic haze exists in Titan. And haze can shield life from UV radiation. And I'm going to focus on this third point here, because UV, stars can be very active. And we see with Kepler that many stars, they can produce superflares, which can increase the UV fluxes level. And there are these superflares, they can be up to 10,000 times more powerful than the largest flares in the sun. So they can be very, very powerful, and they can release significant amount of UV radiation, XUV, for example. And there are a debate in the literature of positive and negative sides that's associated with these flares. The negative side is because depending on the energy and also on the frequency of these flares, they can cause potential effects on the planetary atmosphere. They can induce atmospheric loss. And if they're associated with proton events, they can destroy ozone, for example. And we know in our planet, the ozone layer is fundamental, it's very important to absorb UV radiation, especially the most nocive ones like UVC. And the positive sides that people comment in the literature is because for stars that are very low, they emit very low UV fluxes, this UV that comes with the flare could provide the energy for photochemical synthesis on molecules that are interested in the origins of life. But here I'm going to focus on the negative side. So we're going to go look into the negative effects for life. So there are two targets that I'm working here. One is Kepler-96, which is a solar type star. This star is very active. It shows several flares in the light curve detected with Kepler. This is a super flare that is right in the middle of the transit light curve of a planet that's transiting this star. It's also a quite young, kind of intermediate young star. It has an age that corresponds to the end of the Archean era on Earth. At the time, we had the Great Oxygenation event. And the other target is TRAPPIST-1.
What is that age?
Oh, I forgot by head now. Yeah, I don't remember. I need to look in my paper. I'm terrible with ages. Sorry about that. And the other side is TRAPPIST-1. This is a very popular system. Most of you probably know TRAPPIST-1. It has 7 planets that have Earth-sized planets. 3 of them are in the habitable zone, TRAPPIST-1, E, F, and G. But this star is very flary. It has a total of 42 flares that were detected with the K2 mission, a frequency of 0.3 flare per day. And this is one of the strongest flare that we detected it was detected with the K2. You see that it's a very complex flare. It has these 2 impulsive phases. And these flares, because it's so frequent, it could threaten the habitability of these planets that are in the habitable zone because they are orbiting much closer to the host star than what we see in our solar system. So what I did here was to take the flares that were observed in the visible with the Kepler and the K2 mission, and I estimated the UV that's associated with that flare. But we don't have UV observations for these flares. We have only the visible. So I had to use a template for these stars of UV flares in the UV that is taken for the sun, for Kepler-96, and using observations from AD Leo in the case of TRAPPIST-1. AD Leo is an M-dwarf star as well. So once I estimated the UV associated with the flares, I used a planetary atmosphere model for the planets that are in the habitable zone of these 2 stars. And I took a present-day Earth atmosphere, the one with ozone, and an Archean atmosphere. The Archean atmosphere, it has no oxygen, so no ozone. And then I estimated what is the UV flux that arrives in the surface of the planets, and what would be the biological impact for life as we know in our planet. So there are 2 kinds of life that are used here. One is an extremophile, the Nococcus bradyendurans. This extremophile can live in very harsh conditions, and it can survive high UV radiation, while the other one is Escherichia coli. It's a common bacteria. It can live in our gut, so it can't survive much extreme conditions. So this is the result for the TRAPPIST-1 system, TRAPPIST E, F, and G, the 3 planets in the habitable zone. So you see, I focus here only the UVC, UVB, and UVA. I'm not taking the XUV into account. And this is the flux that arrives in the top of the atmosphere. Each different color here is a different instant of the superflare in the TRAPPIST-1. And the flux that's arriving the surface are these 2. This one is absorbed by the primitive atmosphere. So it absorbs everything that's below 200 nanometers, while a present-day atmosphere with ozone, it can absorb most of the UVC and UVB. So you can see the difference here that a primitive atmosphere is not going to absorb large part of the UVC and neither the part of the UVB as well. No, nothing of the UVB as well. So ozone makes a huge difference. But the UV flux of these TRAPPIST planets are receiving is very similar to that of our planet. If you compare the dashed and the solid black lines, is the flux that Earth receives in terms in UVB, UVC, and UVA. So it's very similar to the TRAPPIST one. So what I did here is to compute, to estimate the biological impact. I took the flux dosage for 10% survival of these bacteria that's measured in the lab. So you can see that Deinococcus rhabdovirus can survive larger UV, around 500 joules per meter square, while Escherichia coli can survive only at very low levels, 22.5 joules per meter square. So if you compare this UV flux dosage that for 10% survival of these bacteria with the fluence that each planet receive, what we find is that these bacteria, in the case of the Kepler-96 system, they only would be able to be in the surface if there was ozone in the atmosphere, absorbing most of the UVC. While in the TRAPPIST-1 case, it's better because you saw that the UV flux is more similar to that of our planet. So these bacteria could live in planets F and G, especially Deinococcus rhabdovirus would be totally fine in planets F and G. Doesn't matter if there is ozone or not. While Escherichia coli would need ozone. Escherichia coli can't survive with ozone, so it needs ozone. And what about if there is an ocean in these planets? We don't know, but what if there was an ocean? So in the case of Kepler-96, the ocean, the water could attenuate the UV flux for that goes through that's transmitted in the ocean. So these bacteria could live under the ocean surface. In the case of Escherichia coli, 20 meters under the ocean surface, and Deinococcus rhabdovirus can live closer to the surface, 12 meters. And for TRAPPIST-1, Escherichia coli could be at 9 meters in the ocean, and Deinococcus rhabdovirus doesn't really need to be under the ocean, so it's fine, it can be in the surface. All right, so directions to the future research based on all the work that I present here today. First, we saw that highly radiated super-Earths are very likely to lose their atmospheres due to atmospheric escape like photoevaporation. And we need more investigation of how likely it is for these planets to develop a secondary atmosphere. And also we need more investigation to know how many of them can remain with some remnants primordial envelope as well. Because then we could use these targets for future observations with James Webb. We can also take more advantage of Hubble to understand about haze in exoplanets. And we know that there is the instrument TESS that can provide that to us, and haze they can be used to probe secondary atmospheres, what we saw in the J1132b. But also haze and clouds are very important because they can mute spectral features in the infrared, in the near infrared. So we need to understand more about them. And we need a better understanding of habitability as well. We see that stellar activity can play a key role into the atmosphere of the planets due to all the factors that are associated with the stellar activity, like flares, super flares, or even CMEs, coronal mass ejections. So we need to understand the role of these phenomena, the stellar activity phenomena, into keeping or stripping the atmosphere of the planets as well, and what would be the consequence of that for habitability. Thank you very much, and I will be open for questions.
Questions, anyone? Yep.
So, just a simple question. I mean, highly irradiated super-Earths, I understand that, but we don't have any information to say that they're the only, sub-Neptunes are in fact near stars, as opposed to at the radius of the Earth's orbit, for example.
Oh, we know their orbit. We know what is the orbital period, so we know that they are very close.
Is that a selection effect of how we found them?
Sorry?
Is that a selection effect of how they were found?
Well, it's a bias of the observation, actually, because most of these exoplanets that we are detecting now with Kepler, they are detected using the transit technique. So it's a bias of the observation because they need to be close. They are close orbit planets in order for us to see multiple transits.
But this is not to say that all sub-Neptunes have lost their.
No, this is basically, it's based on the current population of exoplanets.
Tony?
So for the planets, like you were talking about earlier on, that were kind of Earth gravity-like, but it needed some sort of hydrogen replenishing. Presumably the hydrogen's leaving the planet. Can you see any evidence of that at larger radii, that there's maybe a larger cloud of hydrogen surrounding some of these
Oh, like
planets?
ejected from the
Yeah,
planet?
because
Yeah, in this case, it would not be ejected. It's more interaction between the atmosphere and the interior.
okay.
So it's like outgassing that we have in our planet, you know, like outgassing that can release gases to the atmosphere. So it's not atmosphere being blown away.
Okay.
It's just an interaction between the surface and the atmosphere. But
you
yeah,
need to
so this
replenish.
is just this is a modeling, and it's not, there is no observation evidence that there is this outgassing. We just see hydrogen, so we came up with these possibilities of outgassing replenishment.
Okay. All right, thank you.
Okay, Gwen?
Thanks for the very nice talk. So I'm curious about sort of understanding with larger samples the sort of population of planets that have these hazes. And I was curious whether basically what the prospect is for doing that with larger samples, maybe either from the ground, or if you really need spectral information, or if a handful of photometric points would be sufficient so that you could do it with photometry from space. I'm just curious if either of those are sort of plausible routes.
Yeah, there are some people who have worked with the ground-based telescopes in the visible, and you can also detect the haze as well. So you can do it either from the ground or using space-based observations. The only thing is that like for the visible, not all targets you're gonna be able to observe in the visible, especially the M dwarfs is more difficult. So it depends on the target as well. So we have a couple of planets that have observation with the visible with Hubble, like around 30 planets. And we've been working this catalog to see how many of them show this railing scattering, this visible, this slope in the visible, to make more a statistical study of how likely it is, if it is related with temperature or with another property of the planet.
Thank you.
Tony, are there any questions on Zoom?
Yeah, nobody typed it. We also have people can actually. Diane says she's vigorously typing right now. So if somebody else has a question.
I do have a question. So for the planets with the stripped envelopes, do we see a distribution? For example, can you see a planet that is still stripping the envelope, or most of them have already had their envelope stripped for the sub-Neptunes?
Yeah, for the sub-Neptunes?
Yeah.
No, sub-Neptunes, they still have a hydrogen envelope. Right? That's why we call them sub-Neptunes.
The ones you don't know if they started as
the ones that are in
sub-Neptunes.
the transition region. Yeah, it's a great, I think it's one of the main fields in this in our area in the exoplanets, are people trying to understand how likely it is for them to still be showing any escaping. I don't work with the observation of escape itself. Like there are a lot of people, I think Leo, our colleague, works with that, but I don't work with the observations of the atmospheric escape. But it would be great to see if you can detect some of these planets that are in the transition region between sub-Neptunes and rocky planets, and if they're still stripping these atmospheres, or if you don't detect an atmosphere at all, could be also an indication that they don't have it anymore. They already lost everything. Or if you detect, then it's because then you need to understand if it's a remnant envelope from the atmospheric escape, or which means that the planet didn't lose at all everything, it still has something, or if that envelope is a process of something else like geological activity, like outgassing. So there are a lot of factors that can play into role here, and you need to understand this evolutionary process in order to interpret these observations, to understand if you're not really seeing the escape.
Thank you.
So Johanna was curious about the HCN. I guess that's what hydrogen cyanide, is that right? Or
Yeah.
So she was puzzled just because the model, she was curious about how consistent the model is with the data. There were maybe wiggles in the data that seemed to be the same amplitude. as the hydrogen cyanide feature, but they were fit with more of a flat line. And I guess that kind of goes to, and this was for
And go back. to the-
GJ 1132.
Yeah, it is the
Yeah, right here.
spectrum here. The IGCN feature that we see here, it's pretty strong, but
Yeah.
of course, this feature, the methane, I would say, is the weakest one.
Yeah.
And we will need, and this target's going to be observed at James Webb. So we need the James Webb in order to confirm anything that we are observing here with Hubble. There are other studies for the same target using the same data set, but another pipeline that they found a flat spectrum. But we have been working with them to understand the difference between our pipelines. And there are differences in the way that we treat, for example, the limb darkening coefficients, which is the, for those who are not familiar, the limb darkening is the difference of the stellar intensity as a function of the distance to the edge of the disk. So there are differences in the way of the pipelines work, and we need the James Webb observations in order to confirm that, or to say something else. No, there is something else.
I mean, while
So,
you're on
yes.
it, can you say something a little more about how you do the fitting? How extensive, do you search different models, or how do you gauge which model's the best fit?
Yeah, so this model, the atmospheric retrieval that we do here, is basically, it has multiple observers that we can put in the atmospheric model, like water or haze, cloud and haze, methane, HCN. And the model is going to look using a Bayesian retrieval, using MCMC, is going to look into multiple, it's going to use the priors, the data, and it's going to look into multiple possibilities to find which one is the most consistent one. And in this case, it found that haze and HCN was the most consistent with this data. But as I said, we need, again, more observations in order to really confirm that or refute that. But if you wanted to look more into the details of the modeling, I'm not the person who did the modeling. It was our collaborator, Gaia Roudier. I would recommend you to look into this paper of the J1132b that you can see here to go more into the details of the Cerberus modeling.
One last question from Johanna. She was curious whether Excalibur will be open source or just the data products will be open.
Yeah, it's going to be the WST3 data set, which is from 1.1 to 1.6 micron. It's going to be open very, 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 very soon. So the IPAC here at Caltech is the one hosting our pipeline. So we have been working with them in order to make this portal accessible, public to everyone. So I believe that by probably next month, very soon, this portal is going to be open. So stay tuned, or you can contact me, mail me, and I will definitely send you the link once it's public. But it should be very soon. So each of you can have access to the WST3 data set, the transmission spectrum, and also the steps before we obtain the transmission spectrum, like the transit light curve, the spectrum of the star, and even after, also the modeling, the Cerberus modeling, the atmospheric retrieval. So you're going to also have access to all the correlation plots that comes from within the retrieval, and the model itself as well.
Great. Okay, that's a good place to stop. Well, thank you very much.
Thank you very much as well.
Thank you very much on Zoom, and thank you very much, everyone.
Ok, desliga aqui.